We want to draw root locus diagram. First we need to find poles and zeros. We have any zeros. We have three poles: 0, -2, and -4. These are locus starts poles and it's and at the zeros. Uh, First, we draw the diagram. Decide where the root locus exists on the real axis, uh, and we use the following rules. These are imaginary, these are real parts. A point on the real axis belongs to the root locus if the number of poles and zeros to the right is odd. Now we check the interval step by step. Interval between 0 and -2. These are poles. And -4. Poles to right, uh, 0 to 1, all odd. And therefore is interval of the root locus something like this. And interval between -4 and 2, -2, poles to right 0, -2 to 2 poles. Therefore, this is interval is not on the root locus. This explains why there is a gap on the real axis. Uh, Assumptions direction of the branch, because there are more poles and zeros. Some branches goes infinity. This branch follows straight lines and called asymptotes. If we want to find asymptotes, uh, sum of poles minus sum of zeros or poles number minus zeros number. We have is 0, -2, and -4. These are -6. And we have three poles, 0, zeros, and we find -2. Yeah. All asymptotes pass through the -2. Something like this. Maybe. We need to find an angles. Theta eşittir equals to okay plus 1 multiply 180 degree over number of poles minus number of zeros. Our degrees and 60 degree, 120 degree, and 300 degree. Something like this. This and yeah, this and this. And this shows the directions which branches go to infinity. The breakaway point. The breakaway point is the real axis poles not to throw each other and meet and leave the real axis. If you want the feedbacks, we need to write uh, add the feedbacks. If you multiply the holdings, you find equals to 0. We show the other sides. K is equals to minus 0 over 3 plus 6 square plus 8s. the breakpoint is gain k is a maximum or minimum. If we the variance equation, we find the s is minus 0.845 and other s is the root is minus 3.15. But we haven't any roots on this side. We not use this. We use this one, and this is something like this range minus 0.845 r times pass through this one, and we have 120 degrees are between these balls thing. And if you throw something like this, this is going infinity. These ones are going infinity too. If you run this code in MATLAB, you see something like this. This point is minus 2, this point is 0, this point is minus 4, and this point is 0.845, and this is the diagram. We analyze waveform from left to right and determine the type and components values of each stage. The first amount, we observation the input constant DC value 1 and output constant DC voltage opposite sign. And if you analyze this, both of them, the output is inverted scale by the constant factor related to input. Therefore, this stage is inverting amplifier. If we find the gain for this, RF or R1. So let R1 be input resistor and RF is the feedback resistor. If we want to do the calculation, we find 0, minus 0, minus 5. Choosing parameters. If you choose R1 is 10 kilo ohm, RF is 5 kilo ohm. Any resistor paired with the same ratio is acceptable for this stage. If we next one for next op-amp, we observation the input is 1 voltage and output is 0 to 4 voltage, and the integral of the constant is a ramp. Since the input negative the output slope is positive, the circuit must be an inverting integrator, this one, and the output increases from the 0 to 4 voltage in 4 seconds. First, we need to find the slope 4 over 4 is 1 volt over second. Circuit input resistance is R2, feedback capacitor is C2. Integrated equation is V out equals to minus 1 over R2 multiply C2 integral V in T dt. If we make this question equals this V out equals to 0.5 or R2 RC T, R V in is 1 0.5 is in here, and when we do this, because this is equals to 1 and R2 RC equals to 0.5 as we choose the C2 is 1 microfarad and R2 is 500 kilo ohm. Our last stage is input amp signal with slope, and our input is 1 voltage, our output is -1. The derivative of a ramp is constant since the input slope is positive and output is negative. This stage is inverting the differentiator. Circuit's input capacitor C2, feedback resistor is R3, V out equals to minus R3, C3, variance in over dt. Since variance in or dt equals to 1, minus 1 equals to minus R3, C3 multiply 1, shows us R3, C3 is 1. Yes. C3, we choose the C3 is 1, but R3 is 1 billion ohm. Now instead consider the circuits are parallel, connected parallel, and their outputs are sound using the unity gain summing amplifier. H1 is minus 0.5, H2 minus 1 or R2 C2S C2S equals to minus 3 or S H2 equals to minus R2 3 C3S equals to minus S. Since the blocks are imperial and sound, when we sound these ones, minus 0.5 minus 2S minus S. If we simplify that, this is our final transfer function. This transfer function compresses the executive pin controller and 0.4 operational gain. KP react present error 2 over S is integral gain K1, accumulated pass error and states error. S is predictive behavior and reduced overshots. That's all. If we run this code, we send this graph. Given system, open loop transfer function. Since the unit feedback system is HS is equals to 1, system type and continuous state error. This specify the type of system. Type of system determined by the number pure integrated in the open loop transfer function. This corresponds to the number poles to the origin S is equals to 0. Analysis. I have uh, look at the generator GS. Our GS is S multiply S plus 5. This is the standalone S term. We have one type system. Calculate the state error ESS for the unit step input. For a unit step input, RS equals to 1 over S. State error depends on the static position error constant KP. ESS equals to 1 over 1 plus KP. KP equals to limit GS 0 equals to limit 10 or s multiply s plus 5 equals to infinity. Since the PP is to infinity and also ESS is equals to 0. We find ESS is 0. Uh, if unit ramp input is implied from this test later, for a unit ramp input RS is 1 or equals to 1 or s square. The error depends on static velocity error constant QV. ESS equals to 1 or QV. First compute QV is equals to limits S go to 0. SGS equals limits S go to 0. Then S or S multiply S plus 5. QV equals to limits S to 0. 1 or S plus 5 equals 10 or 5. This means 2. ESS equals to 1 over 2 is 0.5. Find natural frequency and damping ratio. We first derive the closed loop and characteristic equation, deriving the characteristic equation 1 plus GS equals to 0, 1 plus n over S multiply S plus 5 is equals to 0. Multiply both sides S plus S multiply S plus 5. We find S plus 10 equals to 0. Square plus 5 S minus 10 plus 10 is 0. Compare this with the standard second order equation, and this means S square plus 2 omega Bn S plus Bn square. Natural frequency. Comparison matches the constant term. Bn to Bn square is equals to 10. Vn equals to plot 10 is equals to 3.162 radian over seconds. The impression ratio is 2 omega Bn equals 5 to 3.162 equals 5 omega is equals to 0.79. Conclusion on system behavior. Since the system is under damped, this means for the step unit output will overshoot the desired value and exhibit occlusion before setting the final steady value. If we see in the MATLAB code, if we run this code, we see in this unit step response.